a few more people rolling in, but we can get started. So welcome everybody to the July 6th working group on multiscale modeling in viral pandemics webinar. No, my keyboard's not working. Okay, here we go. This group is co-led by myself and James, and of course we have Jim Sluka and Lorenzo assisting with the infrastructure behind our webinar series and everything we do. So thank you all for your help. As always, we have a number of social media channels, so feel free to repost and tweet at us and contribute to our social media presence. For announcements, Indiana University has 2 open rank professor positions related to biomedical digital twins. These are senior professor positions. If you have any suggestions or are interested in these positions, please check out the website or email James with any questions. Also, as you may know, this working group has grown, also expanded into the Global Alliance for Immune Prediction and Intervention. Please take a look at the website if you're interested in joining and becoming a member. Please sign up on the website and help us also spread the word about the organization. Any other announcements? Okay. We will have the IMAG MSM working group and GLIMPRINT steering committee meeting tomorrow, and we'll be summarizing and discussing the IMAG MSM NIH meeting from last week, and we'll also be discussing the European Digital Twin Consortium call for feedback on their roadmap. They're asking for feedback by July 15th. So the timeline, the turnaround here is pretty fast. And so it might be a good idea for the steering committee to discuss that and potentially figure out a strategy if we want to provide some group integrated feedback on their roadmap. July 13th the next 2 webinars will be July 13th and July 20th. July 13th, if Reinhard and Anna are still available, they will talk about the Immune Digital Twin workshop that happened in May, I believe. Time flies, in Paris. And also, please use this URL if you have any suggestions for speakers to present during our Thursday webinars. So with that, it's my pleasure to introduce Tom Yankeelov, who will talk about his implementation of medical digital twins in the context of breast cancer and using MRI-based imaging to predict response to breast cancer therapy.
All right, good. Okay, well, thanks so much for this opportunity, and I sincerely hope I don't bore you too much, and I hope that you enjoy it. If you have any questions at any time, or comments, or cries of joy, or shouts of misery, just let them fly as we go here. I'm going to start out in left field, and I'm hopefully grab your attention. So, in the 1940s, the U.S. Air Force tried to make a seat to fit the average fighter pilot, and they were having all these difficulties. There were all these wrecks that were happening. And it was widely believed that the engineering was fine. It was just that the pilots were so constricted that they weren't able to maneuver the aircraft. And so they hired this young scientist, Gilbert Daniels. He had just recently graduated from Harvard and was obsessed with making measurements about people's the dimensions of various body parts. His senior thesis was, in fact, on the size of people's hands in the Harvard graduating class. So they made this list of 140 different dimensions, thumb length distance from ear to ear, et cetera, on more than 4,000 pilots. And then they focused on the top 10 dimensions that everybody thought were going to be the most important. And they found the pilots who are within the average of these 10. The idea being that if you could find what the average pilot was, then you could build the cockpit to fit them, and then these issues would subside. So average was defined in a very, very liberal way here. It was defined as the mean plus or minus 30%. So we have now reached the first part of audience participation for today's performance. As of the 4,000 pilots, how many do you think fit into this average 10-dimensional space? This is a question for you, the home viewer. What do you think? What number? And I can't go forward until someone says a number.
Half.
Half. This is half.
Zero.
Yes, so 0 fell within this average 10-dimensional space. So he's had this really snippy comment. He said, if you design the cockpit to fit the average pilot, you're going to design it to fit no one. He says, once we showed them that the average pilot was a useless concept, they were able to focus on fitting the cockpit to individual people. So nowadays, the cockpits are designed to have all these different things that you could use to maneuver them so that they fit pilots who are within the 95% confidence range of whatever the dimensions are for how tall and heavy a pilot can be. I'm not an expert in this area, of course, but I've been told that this is what started all the adjustments that you have in your car seat. Was first came from these studies on trying to make pilots comfortable in the cockpit. So the take-home point here is that any ranking that's based on averaging unconnected quantities is going to be severely limited in its practical utility. And this brings us to my clinical trials. And my infinite wisdom, what I see is the fundamental issue with clinical trials. They identify the intervention that works best only for the population. But of course, there's no average person. So if you're finding the therapeutic regimen that works best for everyone, then you're really finding it that works the best for no one. And sometimes this kind of comment really irritates people. But since the whole goal of a phase 1 through 3 trial is to find some therapeutic regimen that's going to work better than the standard of care. And better is defined by more patients in the two populations who had a better outcome. And so it's just a population-based bulk average. So statistical inference, of course, it's enormously powerful, but it does rely on properties of large populations that can obscure conditions specific to the individual. So these high consequence decisions, like those that are in oncology, have to be based on more than just data analytics. So they have to incorporate the underlying biophysical processes that you then mathematize, if you will, and then calibrate it with patient-specific data to make patient-specific predictions. So how do we do this? Well, so I was told to prepare about 30 minutes, so I see the next 25 minutes going like this.
You're muted, Tom.
Have I been muted the whole time?
No. It just as you switch to the slide, you went muted.
Oh, interesting. Okay, well, I'll try not to do that anymore. I guess maybe my cursor was right above it. All right, so I'm going to give a quick summary of 2 different kinds of MR measurements. There's a host of other ones, but for the time constraints, we'll focus on these 2, and then we'll try to use those to build these biology-based mathematical models, and then show how we're going to use those to power digital twins and hopefully work towards N=1 clinical trials. And if you get super bored, there's a counter down here. We're going to make it up to slide number 37, and we're already at 8. Plus, there's like an acknowledgments and a thank you slide. So really, we're practically done. All right, so there's this thing called dynamic contrast enhanced MRI. And the goal here is what you do is you park yourself in a region of interest. We've done that here. We have a sagittal view of a woman with an invasive ductal carcinoma right here. The nipple would be here, chest wall's over here, and you can see the beating heart that's over there on the right part of the frame. And so you take a bunch of images before, during, and after you inject a contrast agent. And as the contrast agent perfuses into the area, it's going to enhance the tissue to a degree on how much gets there and then how long it remains. So the breast is actually a really nice place to do this kind of measurement because all the adipose tissue is storage. It's poorly vascularized, so it doesn't enhance at all. The fibroglandular tissue does give you a little blush, but the tumor right here obviously really lights up. And as this cycles back around, you'll be able to see it really pop up. Right there, boom. So the idea is in your mind's eye, if you pick one of these pixels that's in this tumor here, and in your mind's eye, there's baseline signal intensity, contrast agent comes in and then it increases. The signal intensity increases, and then it'll wash out. And you can analyze that with a pharmacokinetic model to extract these different parameters that report on tissue characteristics. So here's one little map that you can make. This is of blood flow, something proportional blood flow, and this is in breast cancer patients who are undergoing neoadjuvant therapy. So that just means pre-surgical therapy, and in this case, you're imaging the patient at baseline before this therapy starts, and then in this case, one cycle later. So that's about 2 weeks later, depending on sort of when weekends fell and stuff. And so here's the map at baseline of someone who responded. Tumor size is here. The red and yellow indicates the high blood flow areas. The blue indicates the lower. And then a couple of weeks later, you see there's been a pretty big reduction in blood flow, although the tumor size hasn't changed very much. And that's kind of common, that the tumor size is temporally way downstream from the underlying physiological, cellular, molecular scale events. So this is reporting on some kind of response sooner than tumor sizes. So you see here, there's been this reduction in blood flow as opposed to a non-responder, where if anything, there's this increase in blood flow. And so in this neoadjuvant setting, this pre-surgical setting, what you're trying to do is predict who's going to have a no residual tumor at the time of surgery and who's going to have residual tumor at the time of surgery. And that dichotomous decision is actually very predictive of 5-year survival. So if there's no tumor left at the time of surgery, it's called pathological complete response, and those patients have a fantastic 5-year survival. It's practically curative. Whereas if you have residual disease at the end of this neoadjuvant therapy, then you're at greater risk for recurrence and even death. Unfortunately, the pathological complete response is achieved only about 30% of the time. So the whole goal is to figure out as early as possible in this neoadjuvant therapy which patients are going to respond and which ones aren't. So then you can try another therapeutic regimen if the prediction is that they're not going to respond. So just to show you that this is useful on its own, you do the ROC analysis on however, there's I think about 50 patients in this study. This is now old news. The area under the curve for using this measurement for being able to predict who is going to have a response and who was not is about 0.77. And actually, this kind of analysis is now used in the I-SPY trials, which is a national platform trial that's been going for, good grief, maybe 15 years now. The other measurement I wanted to tell you about is this thing called diffusion-weighted MRI. And here, the idea is that you have a water ball and water is diffusing around with some sort of characteristic time constant. Now, if I put barriers in that water ball, water will not diffuse as far per unit time because it's bumping into barriers. So with that sort of picture in your mind's eye, you go here and you have this is supposed to be a little pixel here, and these are cells. So when there's lots of tightly packed cells like you might have in a very cellular tumor, you can measure this what's called the apparent diffusion coefficient, and it's going to be pretty low because there's a lot of boundaries here, a lot of barriers to free water diffusion. But if you give some sort of cytotoxic therapy and it works, then you're going to kill a lot of these cells, they're going to lyse, and then there's going to be a lot more space out here. And this distribution is going to shift to the right as indicated here. And so people have developed MR measurements to look at this. And so here's an example, again, sagittal cross-section of a woman with a rather large tumor right here. Down here in the red, there's lots of pretty free water diffusion. So this apparent diffusion coefficient is a higher value. The value would be about 3 × 10⁻³ millimeters squared per second for a water bottle at 37 degrees C. So this is pretty freely diffusing water here. But up here where the tumor is, there's a whole bunch of cells, like in this picture, this little cartoon here. And so the apparent diffusion coefficient is way down. And so the hypothesis is if you're giving treatments that's killing off these tumor cells, then the ADC will go up because there's less barriers. And so we did this a long time ago, and this is kind of what was found. Here we have a tumor right here. A couple of weeks later, there's now a bunch of red pixels indicating the apparent diffusion coefficient went up. The interpretation is the number of cells went down, so positive response. And here in the non-responder, there's hardly been any change at all. If anything, there's been an increase in the number of cells there. So if you do the ROC analysis on this, you get an area under the curve of 0.81. And of course, the measurements for the contrast enhanced stuff and the diffusion stuff here, you could do them in the same imaging session. So why not combine them? So if you combine the measures of perfusion and cell density, then you can correctly predict who's going to have that pathological complete response after the first cycle of neoadjuvant therapy about 88% of the time. So this gives us some confidence for using these parameters in building them into mechanism-based models. So all that stuff that we just went through was just to tell you about the 2 measurements that we're going to use in our more mechanism-based models. All right. So the metaphor that we always tell is that just as satellites provide the data for weather forecasting, we use these quantitative imaging data to provide data for tumor forecasting. So just like you might have a global map of humidity or temperature gradients or pressure gradients or whatever to go into a weather model to make a weather forecast. We have things that tell us about perfusion and cellularity and other things to go into a tumor model to make a tumor forecast. And in fact, if you get nothing else out of today's presentation, which I understand is entirely possible, and I apologize, you might just pick up this little perspective that we wrote almost 10 years ago now on trying to build a science of tumor forecasting. And really, since we put this together, we've kind of just been slowly stealing ideas from meteorology. All right. So now maybe I should just say, is there any questions about the types of data that we're using, or any questions about anything I've said so far before we go forward? All right, I see one thumbs up and two thumbs up. Okay, also looking at people's faces here in the picture, I can tell that James is uninterested. He's looking down at something, and and then Jim Sluka, he's not buying it. I can tell from his picture he's not buying. But Slim looks like he's pretty happy to be here, so that's good. Take that. All right, so these are the two images.
I have a question.
Yes. Okay, great.
So you didn't see an improvement by adding like the two parameters. You had like 88% with ADC alone, and when you combine them, you also had an accuracy of ADC, an accuracy of 88%.
I think it was 0.77 for the contrast enhanced stuff, and then 0.81 for diffusion stuff, and it bumped it up to 0.88 when you combine.
Okay, thanks.
Yeah. Sure, yeah. And that 0.88 is going to be important. We're going to need to have that number in our head, so thanks for bringing it up. All right, so now we're going to try to take these measurements and put them into a model. So if you open up chapter 1.1 of any mathematical biology book, they're going to have exponential growth here. And so I don't mean to insult your intelligence here, but just to get some momentum here, we're going to say n is the number of tumor cells at time t, and k is our proliferation rate, right? So the rate of change of the number of tumor cells at time t with respect to time is equal to however many guys you have there times their proliferation rate, and of course, it explodes exponentially. But that doesn't happen beyond early time points. You know, if you put cells in a dish, they will grow exponentially up to a certain time. If you put cells on the back of the hind limb of a mouse, this tumor will grow exponentially. But after a period of time, it's going to start to reach its carrying capacity. So the next section 1.2 in that book is now to take your exponential growth and modify it logistically. So if we say theta is the carrying capacity, the maximum number of cells that you can fit in that dish, for example, then as n gets close to theta, this number gets close to 1. So 1 minus the number close to 1 goes to 0. So the rate of change goes to 0. And this thing asymptotically approaches the carrying capacity. And actually, if you put cells in a dish, they will kind of grow logistically. And if you put cells on the hind limb of a mouse, they will kind of grow logistically. But they don't say anything about the spatial variations in tumor growth. So then you got to turn the pages a few turns there to get to chapter 2, where we introduce the spatial component. And the next thing we do is a diffusion component, right? So 1 derivative in time, 2 in space. We have some sort of diffusion of the cells, and then our logistic growth. So we've gone from exponential growth, tacked on a logistic term, and then tacked on a diffusion term. But of course, tumors don't just expand in a radially symmetric manner, right? There's forces around them. And in fact, when we first started applying this model to tumor growth, the tumors that we were simulating were way bigger than the ones that we actually saw in the animals and in the humans that we were trying it on. So then we had this thought that we needed to couple it to surrounding mechanical properties. And so we did this kind of in the simplest way we could think of. So we took this diffusion of the tumor cells right here, D, and then we exponentially damped it by the von Mises stress here. So we get the von Mises stress by solving this mechanical equilibrium. The divergence of the Cauchy stress tensor is proportional to the gradient and the number of tumor cells. So that's just the differential equation we can solve for sigma, and then the von Mises stress is just a way to turn this tensor into a scalar, and we park that in the argument of this exponential, and now we're going to damp the rate at which the tumor cells are diffusing based on the stresses that they feel. So the tumor cells are going to preferentially go in the directions of least stress, and this is actually borne out in reality. The most striking example we saw when we were first formulating this is tumor cells for gliomas. They will grow along white matter tracks rather than across them, just because it's easier, less barriers going along the white matter tracks than across them. All right, so now we sort of have these 3 equations. One, just the reaction diffusion equation telling us how the tumor cells are proliferating, and then these 2 guys here characterizing tissue stresses to damp the way that the tumor cells are moving. And then the very last thing we do is we tack on this treatment term over here. So this is the same thing, the same reaction diffusion term we saw over here. The rate of change of the number of tumor cells at position X and time T, the rate of change of that with respect to time is due to how they're diffusing, exponentially damped by the surrounding stress. And then our logistic term right here, and then our treatment term, where we have to have some estimate of how the drug's getting there, and then the efficacy right here. So if I do this, this is how they're moving, this is how they're proliferating, and this is how they're being treated. So what we do is we take those two MR measurements we talked about, the one for perfusion and the one for cellularity, and we assign everything we can in here. So wherever there's an N, that's getting from our diffusion MRI measurements, which is estimating cell number, so that we take the ADC measurements from the diffusion MRI data to map to cell number. So wherever there's an N, we can populate that from our diffusion data. Theta, the carry capacity, we kind of have control over that because the natural gridding for this is the size of the MRI voxels. So we know the size of the voxels. And if you have an estimate of the distribution of tumor cell sizes, then you can make a reasonable estimate for how many cells you can cram into one voxel. And so that's what theta is. So that's just a number. How the drug is being delivered, we say to first order, the drug is being delivered in the same way that the contrast agent is being delivered. And as it turns out, that's a pretty good approximation for the small molecules, in particular for the broad spectrum chemotherapies that are used. So that gives us an estimate of how the drug is being delivered. And then this alpha right here is the efficacy. So the alpha of the drug or drugs. The alpha here and this K right here, the proliferation rate, and then this D are all calibrated to 2 imaging time points. Everything else could be assigned from the imaging data, but those parameters I just highlighted, the D, the proliferation, and the efficacy of the drug are calibrated. So we need 2 time points. We get a baseline, and then as early as possible in the course of therapy as we can. The earliest we've done is after 1 cycle of therapy, which is like 2 weeks into a 4 or 5 month long treatment. And so you calibrate the model, and then this is what you want to do. You have these measurements at different time points. And so here is this tumor over time. The red indicates high cellularity, the yellow and the blues and the greens indicate lower. And here's our prediction, and we want to be able to take these two to predict what's going to happen over here. And so here's a little hesitate to call it a movie, but this is what it is. So here is the spatially resolved drugs that comes from here. Every time it lights up, it's going to do a kill down here. And the idea is at the end of this, does it match what's going over here? Okay, let's try that again. So here's our drug coming in. Every time you get a hit of drug, the tumor cells fall apart. And similarly up here, you get your last hit, the tumor cells die. And so the question is does this prediction match what you actually observe at that last time point? And so if we do this over a bunch of patients, this is kind of what we get. So here is just a 3D rendering, and the blue is what we predicted, and the red is what we actually observed. And so the spatial maps are pretty good. In fact, the spatial maps were doing a pretty good job of overlaying the predicted extent of the tumor to what was actually observed. And so that's the measured volume change right here from time point 1 to say the end of therapy. And here's what we predict. And if you plot these guys against each other, compute the concordance correlation coefficient, then it's really quite good in these 139 patients that came from a collaboration we have with MD Anderson. Then if you look at the change in the measured cell counts, that's the N that appears in our little reaction diffusion model from the previous slide. We get a pretty good comparison to how the overall cell count is changing in a patient's tumor versus what we actually predict. And the area under the curve here for separating responder from non-responder is 0.89. So I'm super glad that we had that conversation about what the AUC was before, the 0.88. And so you could very reasonably be thinking, Tom, you just dragged us through a whole bunch of slides and a whole lot of work that took a lot of taxpayer dollars, and you went from AUC equals 0.88 to 0.89. That's not different. The key here, of course, is that 0.88 was for separating populations at the end of therapy based on changes in that parameter, in the diffusion parameter and in the perfusion parameter, the diffusion and perfusion parameter. But here, what we're doing is patient-specific, predicting whether or not they're going to respond or not. And now we have a mechanism-based model underneath the hood. So if you have a model that can actually recapitulate how these tumors are changing in space and time, then you can use that model to try alternate therapeutic regimens. And that's kind of what the rest of this is all going to be about. But I see that there's one hand up. So is that Itamar or Itamar? Halevi, maybe, is the last name? Right? Other people can see that there's a hand raised, right? I'm not just hallucinating.
Yes, you're muted, Tamar, if you're. Okay, maybe not the question.
Okay.
Yeah. Do you hear me?
Yes,
Yes.
sir.
Okay. All wonderful, very nice, of course. But the equation looks to me like some version of Shmulovsky equation. Am I right?
I want to say yes, but I don't remember which equation that it is. The first
It's,
part of it
okay, it's the same
is
family,
ju-
the same form of
Yep.
equation called Shmulovsky. But then, if I remember a lecture that I had about this, there's something called detailed balance. And I wonder if you can specify or describe the detailed balance in the sense of cancer stem cells and
Oh.
cancer dormant cells. So I hope my question is not too complicated, but I'm putting several things together.
Yeah, I don't think I have a good answer for that one. That to me is a very complicated thing because all we're capturing here is the is really just the bulk average of the tumor cells. We haven't introduced different phenotypes of these tumor cells, and we haven't introduced where they're coming from. If they're coming from stem cells or some other or just the tumor cells themselves that are proliferating. So the level
you put population approach and concentration maybe in the usual reaction diffusion equation, right?
Right.
Okay, wonderful. Thank you so much.
I'm sorry.
I appreciate everything. That's fine. That's absolutely fantastic. Thank you.
I appreciate your comment. Every time we try to, when we started this years ago, I came up through imaging science, and so I worked a lot on trying to develop cancer imaging biomarkers, and we kind of got tired of just developing new biomarkers, and we wanted to morph these things together to drive these mathematical models, which was actually my roots coming up through math, physics, and engineering. So we started out by making a list of all the different measurements we thought we could make non-invasively with imaging. And then we started to draw up the most parsimonious mathematical models. And every time we would write down a new term or a new equation, we tried to really tell ourselves we couldn't do that unless we could make another measurement. So if we put in one more species of cells here, then we're almost immediately doubling the number of parameters that we have to deal with, and we may not have the imaging data to characterize it. So we've been trying to keep these models as parsimonious as possible.
That's wonderful. And the red curve here with the zigzags up and down are simulation or measurement?
Yeah, that's just hocus pocus to draw the eye. The dots are the things we actually measure. And we'll talk more about the dots as we go on.
Fantastic. Yeah. I'll shut up. Thank you so much.
No, not at all. Not at all. Okay. All right. So this is mapping things we measured, the cell counts due to the MR data, and then the predicted one. So each one of these points represents a pairing of an actual measurement with an actual prediction. Right. And so we have this area of the curve now, and we have this mechanism-based model that we have some confidence in for being able to predict how these tumors are growing in space and time. All right. So now we're going to try to use these things to do real work. And actually, if you get nothing else out of this presentation, I would encourage you to look up this paper. I had nothing to do with it. This is by Karen Wilcox, who directs our computational institute here at University of Texas, Austin. It's a National Computational Science, and she put together this fantastic mathematical abstraction of a digital twin and then its associated physical assets. So she's in aeronautics, aeronautical engineering, and so their assets are these planes, right? And so basically, there's 6 components, and 3 of them live in the real world, right? Things you can touch and feel and poke and prod. They have these control inputs, the actions or decisions that can influence the physical assets. So how you're going to maneuver the plane, if you've got to call for more maintenance, or if you're going to put in a sensor or whatever. Then there's the physical state of the physical access. So is there a crack in the wing, and what's its length? What's the skin thickness? Those things that you can quantify. And then of course, how you can quantify them, the observational data. Measured strain or accelerometer data, inspection data, flight logs, which might be similar to a radiologist reading an image, their read of the image, same thing for flight logs. So those are the three things that exist in the real world. And then there are three things that are their digital counterparts. So you have the digital states. This makes up, the geometry, the boundary conditions, the things that parameterize the computational model. Then there's the reward, quantifies the overall performance of the asset twin. Was it a successful mission based on whatever the mission was? Was your Amazon package delivered successfully? Whoops. How much fuel was burned? Is it time for maintenance? How much is this going to cost? And then you have your quantities of interest, things like remaining useful life and so forth. So this is a really powerful framework to attack problems in oncology. Our things are a little bit different, but here's a flow chart basically for how we're thinking about this. Patient presents with a physical state, and we're going to index it by eye because we're going to be iterating, right? They have some anatomy and morphology and some mechanical and physiological parameters. And then you can make measurements on this patient, right? I've been talking mostly about imaging, but of course you can take blood work and biopsies, etc. So you have whatever observational data that you have for the system. And then there's the things you can do in the system. You can do imaging, you can take biopsies, you can try to change the treatment, etc. Those are the three things that exist in the real world. Then there's the corresponding digital components, right? And here's the digital state, your finite element mesh, your boundary conditions. Some of your parameters might be things like tumor dynamics, and some of your inputs might be when and how often are you going to give the treatments. So here, this little plot over here, I want to draw your attention to. Right now, for the type of breast cancer that we're talking about today, what happens is you get one bolus of treatment, and then typically there's a 21-day, 3-week waiting period before you get the next bolus. And that's what this is supposed to be describing right here. A big bolus of the drug, vertical axis is concentration of drug, big bolus of the drug, and then it rapidly is removed on the time scale of a couple of days. And then the rest of the time, there's very little drug in the system. So there's very little drug bathing the tumor. But what if you were to take the same total drug and divide it up into 3 bits? Or the other extreme, divide it up into 21 bits and give the same bit every day for 21 days. Now, this is an extreme, and is highly unlikely to ever be practically implemented. Though we do that for radiation therapy, patients get small doses 5 days a week, for 6 weeks, depending on the particular type of disease that they're battling. But unless you have a mathematical model, the only way to test if this is better than this is better than this is to run all of those trials. There's not enough patients and there's not enough resources to do that. In fact, it's even worse because most cancer patients don't get just one drug, right? They get somewhere between 2 and 5, depending on the subtype of their disease. So trying to explore that solution space in clinical trials is ridiculous. It's absurd. It will never happen. So we have to come up with these mechanism-based models to try things on the computer. Our quantities of interest are, of course, are not things like, was the mission a success? Was the Amazon package delivered? It's things like overall survival and progression-free survival. And were you able to shrink the tumor by some amount? And the really nice thing is you can explore these rewards now. If you have a mechanism-based model, you can do it on the computer with patient-specific information to calibrate your model. So here is a dosing scheme right here. When are you going to dose? And then how much are you going to dose at each time point? And then here's a schedule. And here's your predicted outcome from our model that we talked about earlier. This is kind of the same model that hopefully I convinced you is doing a pretty good job of predicting who's going to be a responder and who's not a responder. So like I was saying earlier, once you have a model that you have a fair amount of confidence in, that's doing a good job of predicting response and not response, then you can go on the computer and try a whole bunch of therapeutic regimens and generate one of these surfaces for an individual patient. And what's really interesting about this is we've marked on here the dose and schedule that this patient actually received. And we put on here what the optimal regimen is. Optimal is defined here as a combination of controlling the tumor and then off-target effects, which we're not going to have time to go in today, I don't think. It is very far away from what the patient actually received. And so we see this a lot. Is that back to that first slide I showed you, the therapeutic regimen that's best for the population average is almost never best for the individual. All right, so the patient comes in here with their physical state, we make observations, we build up our model here in the digital state, and then you track your quantities of interest, you try to optimize them to maximize your outcome right here. And then the whole thing goes back to here after you've made your prediction for your reward and you do that intervention, patient comes back, you get another set of data, perhaps because you ordered another imaging study or you ordered another biopsy, and now it's time to reiterate again. So you go to the control inputs to do those things, and then you have a new physical state, and the whole thing cycles over again until you've reached the end of therapy or the desired outcome or whatever. I want to zero in on this thing down here, right? Because this is kind of where the rubber meets the road, if you will. Okay, so we built this physics-based model of fluid mechanics to describe how drugs are getting into the patient. And so with a single injection, this hopefully makes clear what I was talking about. Initially, one big bolus, the drug is really blasted. The tumor is really blasted, but then the drug goes away with with a half-life of a few to 10 hours or so. Whereas if you do multiple injections over time, the tumor is bathed in drug for a longer period of time on average. And so the idea is that you're going to get more tumor cell kill right there. So if we pull those things out and look at them, here's the top row. This is the big bolus, and then it dies here. Basically by 5 days, there's almost nothing left in and around the tumor right here. And so this is how the tumor is changing over time in size. The redder it is, the more drug is there. And then right here is our alternative therapeutic regimen, which is the other extreme, once a day for 21 days. The area under these two curves should be the same. So it's the same total drug, but you can see that over time, this tumor has more red and orange days than it does the yellow days. And so over time, you're getting another, whatever this is, 55% reduction in tumor size, just by giving the same drug in a different way. So we're not talking about switching drugs or even switching order. We're just saying everybody's pipes, if you will, are different, and the way that their tumor is responding to therapy is different. So this one size fits all for treatment is just not going to fly. So we've taken this a little bit further with them, and I hope I'm not beating a dead horse here. I hope this is, we've been at it now for like 30 minutes, so I hope it's still of interest. But here is a really specific change, because we've been talking to clinicians now for quite a while about what they're willing to change in the clinical setting, and it's actually quite limited to what they feel comfortable changing. So we are looking at these 3 drugs: paclitaxel, adriamycin, and Cytoxan. We're just going to call them A, C, and P. It doesn't matter. Call them Tom, Dick, and Harry. Doesn't matter. So at least for the purposes of this, these are 3 cytotoxic therapies, and how long you're going to use to give the treatment for this drug, and then these 2 drugs are given together, and this is how long you're going to give the treatment there. So physicians told us they were comfortable distributing the drug within this time frame for the paclitaxel and within this time frame for the AC. And so we can do that. We can make these surfaces now. If we say we're going to give 4 cycles of AC plus 4 cycles of the paclitaxel, that's the blue curve right here, the blue surface. Or for this green one, 4 cycles of AC all the way up to 12 cycles of paclitaxel, and that's the green surface right here. This gray surface right here, everything below this, the patient is predicted to achieve a pathological complete response. And everything above this, the patient is predicted to have residual disease. This threshold, incidentally, this horizontal plane here came from a whole other study we did where that was the threshold, that was the cutoff for determining who was a responder and who was not. And this red thing here, I have to put on I am now old enough where I have to say I have to put on my readers. The red one is right here. Actually, it's up right here in the corner. So this is what the patient actually landed on with their therapy. These other ones are example standard of care options that the physician said they would be comfortable giving. And 3 of these 4 actually are predicted to get the patient a pathological complete response. Now, this is all simulation with the exception of this red dot up here, which is reality. But this simulation is based on this model that I hopefully convinced you is doing a pretty good job of predicting how these tumors were going to respond in space and time with that area in the curve of 0.89. So this just says in words what I said out loud. The responses are due to variations in the different therapeutic regimens along this axis and along this axis. The responses are the vertical, total tumor cellularity at the end, and that gives us this surface. The light green and blue are responses due to 4 cycles of AC and 4 cycles of paclitaxel. And then the other one was 4 cycles of AC and 12 cycles of paclitaxel. And then the black circles indicate the actual response. I guess that's black, I don't know, it looks red on my screen. And then the gray plane differentiates path CR versus non-path CR. And so you do this for each patient. Each patient has their own surface and they can look very different, right? And here's a case where nothing we could try within the confines of what the clinicians said they were comfortable doing could get this patient down to a path CR. But this one, what they actually achieved is very different than what potentially you could get. Looks like almost maybe a 40% reduction in tumor burden, which would make the surgical target easier. Right. So each patient gets its own surface because they have their own set of parameters and their own response and their own pipes for delivering the drug, etc. So without changing the total therapeutic dose or shortening or lengthening the duration of either ACRP increases the treatment efficacy. In fact, 8 of the patients of the 18 who did not receive a PathCR could be boosted to PathCR, at least in theory. And that's about a 21% improvement in the pathological complete response rate. So let me try to say that again. Of these 37 patients we looked at, 18 of them had residual disease, and this simulation nonsense we just walked through indicated that we could have gotten 8 of them to a PathCR if we'd have used a different therapeutic regimen. When I say it like that, I get shivers up my spine because it's quite nice. So, well, that's, I don't know, that's the result here. All right. So we've been trying to try these things prospectively in animal studies, right? So we developed this framework for model development, calibration, and selection to build a digital twin of these mice that are getting hit with these 2 drugs, right? And the idea is to use digital twin and then the optimal control theory to identify a therapeutic regimen that can do one of 2 things. You want to get greater and earlier tumor control. That's what this is. So this magenta, or whatever this color is here, shows the response for our best experimentally tested therapeutic regimen, right? And then after calibrating our model over these 6 different experimental groups that we did and doing optimal control theory, we found that there was a therapeutic regimen that should have better control earlier and then keeping it stable for a longer period of time. That laid it on one experimental protocol to treat the mice with. And another one was let's say you're happy with this degree of tumor control, but can we use less of the chemotherapy, right? That's the one that's bringing along with it lots of side effects, in particular for this one, a cardiac toxicity. So here we found an optimal control solution that gave us the same tumor control. That's the green line here overlapping with the magenta, which is the same one over here, but only using whatever this is, about 57% of the total doxorubicin dose that was used experimentally. So this makes 2 very specific hypotheses, which we can test, and actually we're now doing these studies and holding our breath to see if the therapeutic regimen we landed on here is actually going to outperform this one, or if the therapeutic regimen we landed on this green one is going to give us the same control, but about with half the doxorubicin dose. But it's still pretty exciting because this is the first time that I'm aware of that we've built a mathematical model and then used it to identify a therapeutic regimen that could do this or this, and then go and test it to see if it actually holds up. So we're all holding our breath to see how those studies come out. Of course, you don't just do one intervention. You do one intervention and then you wait a period of time and then you do another one. So your data has to be updated and your predictions have to be updated. And so I probably don't need to tell you this group this, but this is Hurricane Sandy. The prediction for Hurricane Sandy, of course, was an enormous prediction success in predictive meteorology. The 72 hours out, where the eye of the hurricane landed was correct within 72 miles. And so this was an enormous success. But you can see some of the early predictions were having things going out to sea here, whereas as more and more data came in and your model was refined, they started to be quite accurate. So we have to do this. So we started applying this technique to cells receiving radiation, where we can get lots and lots of data to try to sort this out. So the idea is you have some cells that are growing in a dish here, and you make a prediction, then you're making your measurements, and now you can make your first calibration to make a prediction going forward, and then you just iterate this over and over and over again to see if you can if you can track the data that's being measured. So here, this global scheme is, we took just a training set of these data. These are cell studies. You can get dozens, hundreds of time courses for cells in a short amount of time. And this global one is, we had a training set, calibrate our model to that, get those parameters, put it over here in the test data set, and this is given its initial conditions, and this is the prediction it makes, this green line here, which is very different than what the dots are. And then this is with the data assimilation approach, where you're updating about every 24 hours, I think, for this. And so you do a much better job of tracking the data, and it looks like it's probably time for another update because this is now sailing off of where the data is over here. And so this is just an example in 2 different cell lines, lots of these predictions. Sometimes the global assignment works. Sometimes you do get some cells that are average in some sense and growing with the population, but lots of times you don't. Lots of times the individual grows quite differently than the average, which is the green one. So this one's really flying off into Neverland. So based on its initial conditions. So the data needs to be continuously acquired so your models can be updated. All right, so you've done it. We're practically there. I hope you don't want to stab me in the face. So this is the summary, but this is where I cheat a little bit and I put in one slide to tell you about some other stuff that's going on in the lab, just so you don't think it's all just this one project. So we have these clinical projects. The stuff that I've shown you in the breast is also being applied to the brain and prostate, and most recently cervical cancer, right? Because the models themselves don't know what disease you're looking at. You just need to be able to get the right data, and these are the places we've landed so far. We're also looking at trying to combine these mechanism-based model with neural networks so we can do predictions from time point 1. Now we need at least 2 time points to calibrate the mechanics, the dynamics, if you will. So we're trying to link it with a neural network and a training set to do the prediction from time point 1. We're also trying to predict the distribution of radiolabeled liposomes for glioma. We're trying to develop these techniques in the preclinical setting for time-resolved microscopy, trying to come up with new imaging measures to report on hypoxia so we can inform our radiation treatment models better. We've just started modeling the effects of immunotherapy. I think we have our first paper in revision right now on this. So this is a recent development. Lots of problems here, as you guys probably know. And then there's theoretical projects. We do a lot of unsexy stuff on model selection and identifiability, trying to study the limits of predictability. How far can you predict out before you need to measure again? And then trying to balance treatment efficacy and toxicity. So the summary, optimizing outcomes relies on considering each patient's unique characteristics. This can be achieved through mechanism-based modeling, digital twins, optimal control theory, and data assimilation. So the whole point, this guy we met at the beginning, Lieutenant Gilbert Daniels, he said, when I left Harvard, it was clear to me that if you wanted to design something for an individual human, the average was completely useless. So if you want to design, a therapeutic regimen for an individual patient, you got to rely on their unique characteristics because they're so different. We're so different from each other. But now there's a suite of mathematical techniques that are kind of practical for this. And so hopefully the field will move in this direction. It's kind of inevitable, right? If you look at the history of science, once we mathematize something, we get pretty good at it. Cardiology is way ahead of us in oncology for this. This is where this is going to happen. Of course, these are the people who do the work. I just sit in the corner and worry about budgets. And thank you so much for your time and attention. And I'd be happy to chat with you about this or try to answer any questions or whatever.
Thank you so much, Tom, for a great presentation. Any questions? So I have to say, even if that was your only project, that's quite impressive. So
oh, thanks. Thank you. It's a lot of people working for a lot of years. Yeah.
Lucas has his hand up.
Yeah, hi, Tom.
We'll
Thanks for your great talk. There were so many topics that you covered, and I probably have more than 5 or 10 questions, but I wanted to focus on one aspect that I'm also very interested in, data assimilation in biological systems. So what data assimilation approach are you using? Is it an ODE model combined with a Kalman filter, or what is the method that you use in this context?
So we in the clinical setting for the patients, we're really kind of starved for data. I had to go back and review the whole Kalman filter, and it seems to me that you kind of need borderline a steady stream of data pouring in to really use that. So it's really good for meteorology, where if you're getting pseudo or continuous data from satellites or weather stations or whatever. But in the clinical setting, the brain cancer, we get the most images, and that could be 10 MRIs over the course of several months. So that's going to be hard to do. In the time resolved microscopy data, we get tons of data. We get data every 4 hours for a couple of weeks, and so you can potentially do that. So this is a long-winded of saying that our data assimilation approach is really quite simple. We start with we have a training population that we calibrate our models to, so we have distribution of our model parameters. Then we bring in our test data set and we see what their initial conditions are, and we try to match them to the subset of our training set that looks the most like this guy, assign their model parameters over here, and let it rip until our first measurement. Then at that measurement time point, we now have 2 data points over here, so we can calibrate our model to get parameters over here. But since there's just 2 data points, we don't have a ton of, you may not have a ton of confidence in that thing. So now we have this data over here from the training thing, and we now do a weighted average between the subset of the training population that matches this guy plus their parameters that we got from their calibration. And as this patient goes further and further into their therapeutic regimen, you weight their parameters more and more. So the data for this individual is being assimilated to slowly squash out the population and increase the individual.
And maybe a quick follow-up for the confidence bands. Is it based on, are you using some kind of prior distribution in these simulations? So do you add some prior knowledge to estimate these noise levels?
Yeah, that's a great question, and that is something that keeps us awake at night, and nobody ever cares about. So thank you for asking. There's a number of ways to do this. There's error on the experimental side, right? So we did a whole bunch of retest studies on the imaging measurements that we do. So you put a patient in, you scan them, you take them out, they go for a walk, and you put them back in, and you take another measurement. And what's the error in the measurement there? So we did a whole bunch of those studies for the measurements that we use in our models. And so that's, depending on the measurement, it's an error as low as 3% up to about 12%. So that introduces error there in our measurements. So when you calibrate your model, you got to do a bunch of calibrations based on the measurement you made, plus or minus that 3% to 12%, depending on which measurement you're using. So you have experimental sources of error. Then you also have error in the model. And so when you talked about priors, we do some Bayesian calculations. We're doing it more and more. It's of course so computationally expensive for some of the larger tumors that we haven't completely gone that route. But you do have a prior distribution from your training set or your previous studies to input as your priors, so you'll get a distribution out on the other end, and so that can lead to your confidence intervals as well. So I feel like I said a lot for a very simple problem. Sometimes we track our confidence intervals are based on experimental error, and sometimes it's based on priors from a training data set, and we let that go forward, and then sometimes we try to figure out intelligent ways to combine the 2 sources of error. There's a lot to talk about. If you have ideas about that, then we should schedule a conversation, because I'm sure we're not doing it right. Yeah.
Well, thanks a lot. Yeah, no, that's very helpful. Thanks.
Thanks, Lucas. Yes. Is it? I'm sorry.
Uduak, that's okay.
Uduak, that name is awesome. Uduak, yes, ma'am. Talk to me.
Well, thanks for a great talk. I really enjoyed listening to you and seeing all the work you've done. I just have a question with regards to resistance. So when we look at different treatment options for cancer, most of the time is the cells evolve to develop evolve resistance to the medication. And then I'm wondering, are there ways you're looking at or already doing to build that into your models?
Yeah, that is a fantastic question. And so this is another thing that keeps us awake up. We don't get much sleep. We're worrying a lot. So I mentioned earlier that right, the whole problem with cancer, of course, is that it's such a heterogeneous disease. It's just not one cell type in the tumor, right? You have multiple cell types with multiple response profiles. So if you were to simplify it and say there's going to be cells that are sensitive to the therapy and cells that are resistant, now we have 2 PDEs, one for the sensitive guys and one for the resistant guys. And they likely have different migration profiles and certainly have different response profiles and probably have different proliferation profiles, which means you're doubling the number of parameters that you have. And you may not know the initial conditions. You may not know initially how many sensitive guys you have versus resistant, although potentially you could get a whack at that from a biopsy with appropriate histochemistry. So we haven't done this really in the clinical setting. We've done this in cell studies and mice studies where we can interrogate the system 6 ways from Sunday, and we can say there's sensitive and resistant, and we can do that, and that works. You get curves and fits to the data similar to what I showed you. But in the clinical setting, we're having a hard time separating responding cells from sensitive cells. We have built models that have multiple phenotypes, the tumor cells and then the endothelial cells, blood vessels. So how the blood is feeding the tumor. We've built those for our brain tumor models, and that has helped. But as far as different tumor cell types, that's we haven't been able to crack that nut.
And then just pushing it a little bit, when you say you've not been able to crack, what's the major obstacle? Is it
It's the data.
Okay, the data.
Yeah, we don't have the right data to say whether or not what you really want to know is you want to know the fraction of cells at each time point that are either sensitive or resistant. And to do that non-invasively over the whole tumor and then at multiple time points, it calls for an imaging measure, and that's hard to do. That's just hard to be able to do that. I don't know if there's any reliable way to do that, in fact.
Okay.
Yeah.
Well, thank you so much.
Yeah, thank you.
So I got one more question, Tom. Your schedules that the dosing regimens and schedules that you're considering, what's the degree of freedom there? What all possibilities do you consider? Like, are you considering options where you have like different doses every day, or how do you constrain that space?
Yeah. So for the mouse studies, we've constrained it merely within the time frame of the entire experiment, whatever it was, 4 weeks, and then the total dose we could give. That was all it was for the mouse, and then after that, it was whatever you wanted.
So it could be 3 different doses a day, and then skip a day, and
that's right. That's right. And so, but for the clinical situation, I have had so many, just over the last 2 months, I've had so many conversations with. Are there any clinicians on this call? I'd love to get your insight, but there's tremendous pushback on what they're willing to try. Right, everybody wants at least one phase 3 trial, preferably more, before they're willing to try that therapeutic regimen in their patients. So they will really only say, the best information we've gotten was saying, okay, with this drug, we're okay with delivering it over this time frame, but there's no way we're bringing a patient back more than once a week. It's logistically impossible to get that chemo chair reserved. So we're once a week over some period of time, and then the dose you could potentially change as well. Yeah.
So do you propose to the clinicians like a ranked list of the most effective dosing regimens, and they'll go down like no, yeah, we can do that?
So that's exactly what we're doing. We're now designing a prospective trial, because they're starting to get some belief that these models can do what they want them to do. So what you're saying is exactly what we're gonna do. The first thing we're gonna do is we're gonna just piggyback this on a trial they're running anyway, and just give them a report that says, these is the likelihood of response if you continue in this way. Here are alternative regimens, and the alternative regimen, what we're doing is we're going to do the optimal control theory that gives you whatever dose, whatever schema that is truly best according to the theory, and then we'll just do a distance metric from that guy to the suite that they're willing to try, and then we'll pick the one that's closest. And so we're going to give them a little 1-page report that says this and get feedback on, how it strikes them, with the hopes of the next round they'll be like, okay, let's give it a go. We have one clinician who is very much a believer in this. Interestingly, she's in radiation oncology, where they do have a little bit of leadway about how they're doing the beam forming and where they're going to deliver the dose. So it's maybe it's a little bit more accessible to her.
Do you also consider injection versus pill or different types of delivery for a treatment, or no?
Yeah, these are all IV. Yeah.
IV. Okay.
Yeah.
Thank you. Right.
It's not. Yeah.
Sorry.
I think Mitchell was ahead of me.
Oh, yes, I'm sorry. I thought you left, Mitchell. I'm so sorry.
No, you're fine. No, you're totally fine. So this was more at the end. Tom kind of alluded to this, the not so sexy stuff about identifiability analysis. But I feel like with patient-specific models, like that is an important question to ask, especially. So I just wanted to get a little bit more feedback. Like, are you finding that that's an area where you're focusing more time into, or do you feel like as long as I can predict accurately, at that point, that's all that matters.
Now they definitely want to know a percent likelihood of achieving pathological complete response for the breast cancer if we continue on this path, and they want error bars on that. They want you to say that if there's a 47 to 62% chance that this will get a person to path CR. They want the error bars. They want to have a sense of, at least they say they do. There could be information over, I don't know, I'm just conjecturing. But that's what we're going to do. We're going to provide them with the errors because we make a, you get a trajectory of tumor cell number over time, and there's error bars on that, so we can tell them what that is. Yeah.
It's like this, but this is quite ancient like this.
So Tom, let me ask you something I know is dear to your heart. Since you mentioned meteorology, this morning I saw another paper that says that AI-based methods beat the pants off numerical simulation for weather prediction.
What did you say? I missed that. Who beats the pants off of what?
AI-based models.
I don't know. I've seen a lot of papers that say the other thing. I think AI is going to be fantastic for that on the time scale of hours. But in these this is near and dear to my heart, and we're standing on the precipice here of falling into a huge discussion. For problems with enormous degrees of freedom, like weather systems or like cancer, the training data set that you have to have, it has to be ridiculously enormous to capture the individual characteristics of the patients or of the weather system. I just don't see how this is tractable long term. Maybe it's good on the time scale of a few hours, but once you start, a butterfly flaps its wings over the North Pacific, right, and then you get rain in Orlando. I just don't see how an AI is going to track this. This is particularly a problem in oncology because we already tried this, right? If you Google Watson Oncology failure, you're going to get 1 million hits from very reputable journals across all of human knowledge, from Journal of American Medical Association to Nature to The Economist to the Wall Street Journal. Everybody's saying that it was just a total abject failure. Because the variation that we see from person to person cannot be captured in a training data set. A woman just doesn't get cancer. She just doesn't get breast cancer. She doesn't even get triple negative breast cancer. She gets one of the 6 currently known subtypes of triple negative breast cancer. So the training data set that fits that doesn't exist. And then all the possible therapeutic regimens that she could have needs to be represented in hundreds of patients each. And that doesn't exist. And I just feel like this is fundamentally a dead end, and it's upsetting because so much money is going into it. And you guys know this is the Multi-Scale Modeling Consortium. We had one of those grants a long time ago, but they've stopped funding that, right? So this is a problem, I think.
Yeah. So at the beginning, Tom was saying next week we'll discuss the meeting, the Multi-Scale Modeling Consortium meeting that just happened last week at the NIH. And one of the things that was quite interesting is there were a number of program officers there from NSF and NIH and other agencies, and they were presenting opportunities to fund modeling projects separated by AI and mechanistic.
Well, that's encouraging.
Well, no, but the discouraging part was that all except a few pennies basically was on the AI side, hundreds of millions of dollars of programs.
I mean, I scream this from the rooftops. I'm sure I'm making lots of enemies, but every other week we all get a new email from the NIH about a new bioinformatics or a new AI big data initiative. And we can't forget F equals MA. We can't forget what got us here in the first place. So, but that's certainly, hopefully the pendulum will swing back. I don't know. But for now, it does seem like finding a losing battle.
To be loud and collectively loud, and I'm hopeful.
Yeah. Because when you go to these conferences, like I was at a conference in Colorado a few weeks ago, and there's this panel discussion about mechanism and AI-based models. I'm kidding you not. There were 4 people up there. It was me and 4 AI people, and they even put a chair between me and the other 4. We're laughing about it, but it really felt like that those are the proper proportions, 1 versus 4. So I don't know. But, I don't know.
Yeah.
Any other questions? Well, thank you so much,
You
Tom.
hear me now? You
Yes.
hear me?
Yes.
Okay. You cast some doubt, which I share, about the AI capacity. And the question in my mind is, maybe the topological data analysis may help, especially when you talked about the example of data assimilation in weather and climate.
Yeah, there's some there is some very interesting stuff that's going on in topological data analysis. There's a really great group at Oxford that's doing this, kind of state-of-the-art stuff. And I feel like that kind of stuff can really guide us on what are the relevant measurements we need to go after, right? Because everything, not everything, but the overall majority of cancer biology is, you know, omics based. We're going to measure a gazillion things, and that's going to tell us answers. And TDA can maybe help us zero in on the really important ones that we can then potentially build into mechanism-based models. I always go back to the Navier-Stokes equations, right? This is not a microscopic theory. You don't need to know where each nitrogen, hydrogen, and oxygen are bouncing into each other. It's a macroscopic theory, and it does pretty good, at least out to a week. And maybe we don't need to know everything to be able to be good enough with mechanism-based models and cancer. So, yeah.
So maybe together with the Kalman filter, it will be a solid good science.
Yeah, that's an interesting thought. Yeah.
Okay, thank you very much.
Thank you, guys. Thank you so much. Thanks for the opportunity.
Thank you. Enjoy your vacation with the family.
Yeah, it's not a vacation, it's a trip, right? If you have, you go to visit, yeah, right.
I
All right,
understand.
yeah,
Thank
yeah.
you.
Take
Bye-bye.
care. Bye.